Blender 5 keeps dropping game changers. Today we will build a visualization rig, one control rig that ties together bundles and closures, grid nodes for scalar fields and gradients, and repeat zones inside the shaders editor. And all is driven by a single external controller. The project that we will build today is a complete overview of all these new features. Watch. If I change the range, the color map and the color bar gets updated. We can also change the glyph size and the number of ticks. Everything gets immediately updated. The glyphs will be only rendered in the places in which the scalar field is changing. And they will follow the direction of maximum growth. One rig and 3 domains: voxels, points, and pixels. Just download the Blender 5 below and let's start. So let's go and check what is the overall blueprint of this project. We will have a visualization bundle, which is a new feature of Blender 5.0. We will have a set of properties or parameters that will be stored or will be organized together into this bundle. And these parameters we will be able to access from the Torus, which is the geometry that we will use to project the scalar field. It will be also sent to the material. We will create a complex material we are seeing here with some repeat zone and some closures also inside the shader editor. This is also something new for Blender 5.0. And we will create, as we already learned in the past, a scalar field with the grid nodes and with the field mapping the field on the grid with the nodes that we see on previous videos, based on some domain that in this case, in our case, will be just a cubic domain. We will also create the color bar with some logic to convert the values into some mesh, and these are the meshes we are seeing here that are changing based on our properties. So let's start with the domain creation. So this is the we will go to the geometry nodes, and I will explain each of these parts one by one in this video. So since this is a medium-sized project, I will not create the file during the video because it will be maybe too long for a video. So we will just explain what the nodes are, and I will leave the file of the video in the description of this, the file of the Blender file in the description of this video. Sorry. So we will start by creating our bundle. This will have a lot of properties. We can define any property that we want, and we will have the one way to animate or to input these properties from another object, as we will learn. So this is actually a group node group, and here we will create a visualization bundle. This is just a node called combine bundle. Like this one. What we have in this group, we have connected all these inputs to this node, and as an output we will have these bundle. So this is an organized way to just have this combined bundle, which will be our bundle at the end. So from this bundle, we will connect it to this field processor group node, which will be taking the parameters that we have in the visualization bundle, and it will be used in a certain way. In this case, for example, we will use it to compute the range of the visualization of the scalar field, or whatever we want. So inside this field processor, the group node, what we will have is a closure. This closure will take the range from minimum to maximum that we will define somewhere. We will take some threshold to make some mask, and it will take some coordinate that we will call x in. We will do a map range, so we will have everything that we receive from this minimum maximum, and we will have it as converted to 0 to 1, and this will give us this value that we enter, this x input. We will have it mapped in this range, and we will have it just normalized. As always, we will use this evaluate closure node, and the values that we will enter here, so the input of the closure will come from this separate bundle. So we have the input of the geometry node, which was the bundle, and we will have some certain x, and we will separate the bundle. So this is another node that is very useful for the bundles. We will use it to get specific parameters from the bundle that we are entering here as an input. This is how the bundles are used actually. We will have our menu of parameters available here inside the group node just by entering the bundle. This is quite useful. We will have the range minimum, range maximum, and all the parameters that we have defined. So these are here. There are some examples only, but we can define whatever we want here inside these bundles. So we have the parameters of the bundle. We will pass some range minimum, maximum, and threshold. Still, these are just numbers. We will give it some meaning afterwards. And these coordinate, we are passing it here to evaluate the closure. Then, as an output of this visualization processor, we will have this x normalized and some masks. If we compare here, some clamping mask. Here on x, this value x input will be actually the value that we will give as the quantity to be evaluated for our scalar field. In previous videos, we will use this density of the Gaussians, but in this case, we will just use the position, the length position. So we will have a scalar field which has 0 in the center of position of our domain, and it will increase just the length of the radius from the 0, from the origin of coordinates to each point. So it will be just a very simple scalar field that we will have, and it will be normalized through this group node with the closure. Then, as always, to create the scalar field, we will take our geometry, which will be just a cube geometry from the volume domain. We will apply mesh to density grid, the node that converts the domain into a density grid with some voxel size and some density value, and we will convert this grid into a topology in which we are mapping this density that we are entering from our scalar field. So what we are doing here is creating just a scalar field, very simple scalar field, and we will store the name. We will call it simply field. This is everything that we will do. This is our scalar field, our domain, and now we will focus on the torus and how we will project this scalar on the surface of another object, in this case the torus. So now let's go to the torus. I'll just close this. This is just a torus geometry, but if I want to connect this directly to the geometry, I will have just a different torus like this, but I didn't like too much. Actually, the size of this radius with respect to this, it was not nice for me. So I decided to create another torus, and this is what I have here in this group node called geometry. Here it's very simple. I create a curved circle with certain radius. I create curve to mesh, and the profile curve is also simply another circle. So I will create a circle that is displays, or it is projected along another circle. This will create our torus, and this is good because I can have some control on the properties of the torus. So I can have the one I had before, but I can also change it how I want, and this will be also reflected on the final result. So let's keep it as we have it before, and let's continue with the construction of our visualization rig. Now let's discuss about the inputs that we will have. So for these torus we will build two things. First, we will create one material that will have the quantity of the field that we have just defined, and second, we will have the glyphs, the arrows. I put them on the same geometry node so that they have the properties of the torus. Let's start by checking how we can define these glyphs, and then we will check or we will explain the material part. The inputs of these glyphs, so what we will need to create these arrows, will be just the position of the faces of the torus. We will have also the object info, and in this object info what we will have is the volume domain. So we will have the information of the scalar field. This will give us the values of the scalar field. So we will get name grid from this object, and this name grid we will use the name that we gave to the scalar field in the previous step. So we will just use this field, and this we will give it to some group node called Glyphs that we will now check what it means. For the visualization bundle, we will use the same group that we have here, that we have created, and we will separate the bundle. Every time we want to use a parameter from the bundle, we use this separate bundle. In this case, I choose to use this anisotropy scale that will determine the scale or the size, if you want, of this a factor scale of these arrows, because the scale will be also determined by the magnitude of the gradient at each point, as we will see. So let's see this Glyphs group. In this Glyphs group, we will have the arrows. So we want to define which is the geometry of the arrow. For that, I will just use a cone, but we can use an arrow, adding some cylinder as we did on the previous videos. But for this example, I'm using just a cone. And what we'll need to pass to these instances on points is simply the scale. So some parameter that tells how big is the arrow depending on the magnitude of the gradient of the scalar field in the projected in the torus surface, and the rotation. So in this case, the rotation of these arrows will be the arrows will be tangential to the surface of the torus. So they will be placed on top of the surface, but they will be at the same orientation of each face, and it will point towards the direction of the increased direction of the gradient. So this will be, for example, the maximum value. This will be the minimum, and the arrows will go from the minimum to the maximum. And when the value doesn't change, we will just not draw any arrows. How we can do that? So let's go to the Glyphs, and let's start by checking what we do on the scale. So for the scale, we will need to pass the distribute points on faces. We will pass the geometry. We will need to pass also the grids, which will tell the magnitude of the scalar field, and we will pass the position and the glyph size, which is the parameter that we discussed already. And it will give us the geometry, which will be still the torus, and we will give us some scale vector that we will connect here on instances. On points, we will have this scale connected here. On this group node, we will sample the grid. So we will get our scalar field. We will sample on certain values or certain positions, and these positions turns out to be the faces of the torus. So the position that we are entering here, and if we go to see from where this position comes, it comes from here, which is just the position of our torus. So this will be the position of the vertices of each torus, each vertex of the torus. If we go there, then we will pass the position. So what we are doing here is just computing the value of the scalar field on each position, on each vertex of the torus. And this is where we will give as input to the scaling factor of the Glyphs. Once we do this, we will map range. This map range we will give here from 0 to 1, which is the value of our scalar field, and we will give it some value which we want to clamp the arrows. I can place also here 0 to 1, but we will see something like this. The change will be much more noticeable. This we can also do if we wanted. But for now, let's say we can keep 0.05 to 0.1. 0.2 will be this is very small. 0.5. We can keep in mind that the more these values are different, the more visible will be the difference between the minimum and the maximum, of course. It will give us more the impression of the changes of the gradient size. So I will keep it as I had it in the past, which was something like this, which was you cannot see too much the difference between these and the smaller ones, but yeah, we can keep it like this. Then we have this map range, and we will multiply the glyph size, which was the parameter from the bundle, times the value that we get from the scalar field, and this we will pass directly to the scale. So we will combine x, y, z, and we will have a vector, and this vector that is coming as an output, we will connect it directly as scale of the instances on points. So we have now the scale and the position and the geometry of this glyphs. So something here I didn't mention is we will have these distribute points on faces, which will just, as its name indicates it will distribute some points along the faces of the torus. This will be the one that will distribute our glyphs in the faces of the torus. Now we go to the rotation, and for the rotation we will just use the equation in which we can compute the gradient of the vector gradient of the scalar field. We will now project this gradient along the normal. Then based on that we will subtract the gradient minus the projected coordinate of along the normal. So we will have the tangent component, and this tangent component we will rotate towards the direction of the gradient. So this is what we do here. We will compute the gradient with the new gradient geometry nodes from Blender 5. We will sample the grid again on the position, so we will know which is the gradient value on each position. And we will have now to compute the dot product between the vector that we are entering here, which it is actually the normal vector. We will see it from here. What we are giving here is the normal of the distribute points on faces. So this normal we will use. These are the normal vectors of the faces of the torus, and we will enter it here. We compute the dot product, then we can multiply the dot product by the normal times the dot product. So this is the component along the normal. Then we will subtract the gradient minus this vector that we have just computed, the component along the normal, and we will normalize this. This will be the vector along the tangent. So our new our glyphs we will rotate along the x-axis. We will orient this vector, and we will use these two nodes, align rotation to vector, which orient a rotation along the given direction. So first we will orient them along the x coordinates. So this will give us something like everything oriented along this first vector, and then we rotate along the x of the local angle of the glyph to place it on the surface of the torus. So this is what we do. We use the normal vector and we rotate the glyphs along the normal vector in the x direction. So this one here, so just to summarize, this one here places the gradient along the tangent of the torus, and this one rotates it with the normal vector as axis of rotation in the direction of the maximum gradient. So this is what we compute here. This is the direct direction of the maximum gradient, and this is what we will rotate the vector, which is the normal. So we will just orienting the glyphs along the maximum rotation, along the vector, normal vector, towards the maximum direction. And finally, what we will do is creating a mask so that we don't put glyphs in the places in which the gradient is zero, or there is no change in the scalar field. So for that, we will just compute the length of the gradient. It's quite easy. We will create one value, which is a small value. I put this 0.0001, and if the value is greater than that, then I will pass the result as an output node of the of this group node. So as an output, we will just if we have everything ready, the result, this mask, we will set as selection. This will tell that we will select only those glyphs that satisfy this condition. The rotation, we will use the rotation that we compute, and that's all for the glyphs along the torus. Now we will define the material of the torus. So let's go back to the torus, and we will see we will have two materials. One material is for this torus surface, and one material is for the glyphs. For the glyphs, we will not enter into the details. It's just a black material. We can choose whatever we want. But the interesting material will be this material that we are giving here with these rings and with the value of the scalar field as input. So let's go to the shader editor. And let's check this material. So now we will describe how to build the material of this torus. So for that, we will enter an attribute. In this case, it will be the field, the scalar field that we define for the on the domain, which is called field. We will use a color ramp and we will enter it as base color for some closure that we will define here inside. Inside the closure, let's show the details of what the closure will be doing. So we enter the base color and we accumulate some color, or we mix the colors based on some operations that we will do. So this what we will do here is just adding some layers on top of the base color, and these are the layers that we will that we show, that we see actually on the torus. So if we see, we have some color, we have some rings, and something else that we added was some Fresnel refraction, diffraction on the surface of the torus. So yeah, these are 3 layers, and because of that we added these 3 iterations in this repeat zone. So how the repeat zone is built, actually we will use the number of the iteration, and we will create 2 gates. So the first gate, this is the first gate, will check if the iteration is less than 1. Then we have the first layer. So if the iteration is less than 1, we will use, we will combine 2 colors. If the iteration is between 1 and 2, so this is the epsilon. So if it's compared with 1 with so greater than 1 but later lower than 2, we will use this, and if we have it greater than 2 but lower than 3, we'll have this. So that's why we have this epsilon here, 0.5. So let's go step by step. Initially we will have the color, the base color, that we will add it as color, accumulated color. We will mix it here with some white color, and this white color we will multiply it, and the factor we will multiply it by 0.5. So we will combine in the same amount the base color with this white. And what we have here on the first gate will be then combining the base color that we get from the color accumulation. We will combine it with this color that we receive from here, which is the ring mask. So we will have first color, and the next pass from the repeat, we will combine it with what we are entering here as an input of the ring mask multiplied by 0.5. Then in the next, so we will have named this color after bands, which we will mix, which is the color that is coming from the bands, and then we mix the color from the bands with the base color on the next iteration. And here then we have another input, which is the Fresnel coefficient that we will multiply here with some factor, and we will mix the result from here to the previous mixed color that we have. We will mix it here, so previous color with the new, and the factor will be used depending on the gate. So what we're doing here is that if this gate is 0, we will not use it, but if it is getting 1, then we use it, and then we mix it with this one when the gate is 2, and we send it to the color accumulated color here. This we send it out of the repeat zone, and we add it on the closure zone, and the group node group output will be this closure here, so that if we check here, we will just evaluate this closure and we will provide these inputs. So the base color is what we have here for the color ramp from the field, which is the color that we see here. The rings, we will compute them in this node, in this group node group, and the Fresnel is just the index of reflection of the certain material that we will give. Just let's see how the Fresnel effect is affecting our torus. So I will just, for example, change this for 0.5 or 0.8. We see this whitish surface when we look at the torus in a tangential way. Maybe if we put something exaggerated, we will see it even more like this kind of velvet effect. Which is just placed on top of the other two colors that we have. Let's keep it 0.8, something like this. Just to use it as an example of what we can do with these nodes in Blender with the shader editor. But now we are able to use, also similar to the geometry nodes, we have these repeat zones and closures also in the shader editor, which I think will open the possibilities and capabilities of the Blender in terms of procedural materials. Let's check how we define the rings. This will be quite easy, so we will just use texture coordinates. We will use object, which is the torus in this case. We will create something on one node that is called radial tiling. We will define this resolution. If we change it, for example, to something much less, we will see the effect. So this is the amount of subdivisions that we will use to define these rings. And the roundness, for example, if the roundness is 0, we will see some so here I'm using 6 sides and roundness 0, so we will see some kind of a hexagons here. For example, then 8 will be some octagons, and this will determine the amount of segments that we use to define these rings. I had it 0.64, which I think you don't see too much the difference with high or low roundness, because there's a lot of sides already. Then we use the segment coordinates and we separate this XYZ, SYC, and we use the Y coordinate to place it on this on top of the torus. If we use X, it will look along, let's say, perpendicular to the Y. So this will be reduce radial lines from the center outside. This is what we will get. And if we use the C, then this will not show anything, because we are placing the rings in a two-dimensional surface, which is the surface of the torus itself. So that's why we choose Y. That will create these contours. This is quite like a fake contour, because this is just centering some circles here, and we'll go along these circles independently of what the field is. In future videos, maybe we can check how we can, instead of using this radial tiling, which is creating circles, we can actually create some contour plots of the values of the scalar field itself. So, but for this example, for the material, I think we can just keep this faked contours, which work only in this case, in which the scalar field is just a radial scalar magnitude. Then we have this, we multiply this at certain value. If we don't multiply, this will change actually the amount. So if you see 10, this will 5, and this will be the amount of rings that we will have. This looks quite funny, but quite nice. It will be good also to put this as an input of the material, so we can vary it as we want. But for this example, we will just keep it as a coded value here. Let's put something. I had 32, we can put even 64, which I think it will be already too close each other. It looks good, but let's keep it as 32. Then we will add a fraction, and we will map the range. So what will happen if we don't add the fraction? We will not have anything, but because we will have a single value of the radius of the radial tiling along the whole surface. So what we want to do with fraction is actually discretize this value in different number, which is what we are having here. 32, so 1 times 32, and then we just add the compute the integer part, so that we divide this radial field into some discrete integer numbers. This then we can control with the fading of this fraction. We can control it with the map range. So if you see, this is not a single value, but this has some gradient, some fading. This is controlled here by this value that we are mapping. So this is for the fraction, and this will be the, say, the integer value, and then the decimal values, which will be fading here, is what we are mapping here from 0 to 1. If we set 0, then this will complete all the decimals, and if, for example, we added 0.5, then this will start by the end between the two different integer values, and this will be the output range. This will give us the also the intensity of what we see here. So, for example, if we add this 0.8, then we can control the intensity of the gradient zone. Let's keep it as it is right now, but we have possibilities to play with this. And the Fresnel will be just connecting the factor as we previously discussed. We can change here the metallic and roughness properties as always, but we can also keep it as it is, well, as we want. Okay, so this was the material, and we have already defined everything for the torus. Now we will focus on two things that are missing. One is the definition of the color bar and the values here, and the technique to use an additional or external element to tweak these parameters or to control the parameters of the bundle without need of going to the geometry nodes and changing everywhere. So this will be the last part of the video. Let's go to the legend. I will not spend much time on this part. It is quite simple, the definition, but let's take a look on it. So for the legend, we will have two elements. One is the color bar, and second is the ticks. The ticks will have some small marks, so we will see them here. These ticks, and it will have the values of the mapped range into the torus. So let's start with the color bar, which is the simplest part. We will just add a grid with some size and x and y. So this is just one plane, two-dimensional, so one grid. And we will set position based on some offset. So this will allow us to control the position of the plane of the whole legend. And we will add a material. That's mainly it. Let's see how this material is defined. So color material. So we can go to the layout and we open this color bar. So in the color bar, we will just use the generated texture coordinate from the grid itself, and we will connect it to this separate XYZ vector, and we will use just the Y coordinate, which is this coordinate along this direction. This will be everything. We can copy and paste the same color map, and I'm adding here some base color, but also some emission, so that we have some vibrant color on the color bar, some intensity that we can see very good which are the colors. This is all for the color bar. If we add, for example, X, it will be in this direction, and as I mentioned, the C will be just a single value because the C will be in a third dimension, and this is a two-dimensional object. That's it for the color bar. Now let's go to check what is on the ticks. For the ticks, we have some inputs. Again, our visualization bundle. This is important because this will tell the ticks which are the mapping range that we are using. For example, in this case, 0.3 to 0.95, and this is what we are controlling from the external object. And this we will pass it through this group node that will compute the values. This will give us the numbers. We will join this geometry with the ticks, which will be also linked to this ticks number. So this will be the iterations of this repeat node. We already know that the iteration is related to some repeat node, and the ticks will be also some repeat node that we will control from our visualization bundle that is controlling all the parameters that we actually have for our simulation. Sorry, for our visualization. As a group input, we have start location, and these are some, so to the start location, we are adding some offsets to, for example, make the distance between the color bar and the numbers, or the orientation, the location of the numbers with respect to the ticks. If I change this will move the ticks with respect to the color bar. Sorry. And if I move this will also displace this. So I will not change this. These are some fixed values. but what I will change what I can change in the future is the start location. So I will move not only this part but also the color bar. Everything can be set to a different location. So that's why it's important that we put the group node, the input here for the location. Let's start by checking the ticks. This is quite easy. So for the ticks we will have some computations. We will count the number of ticks that we are receiving. So here this is our input. This is the number of ticks that we will have. We will subtract -1 and we will divide 1 or the size of the color bar, which is 0.6, divided by the number of ticks -1. So this value that we subtracted here, we are divided 6 divided this. So this will give us actually the distance between each tick. And we will have this as a y coordinate of the offset of the mesh line. So we will start this location and we will add some offset, which will be that distance, and we will repeat that. We will repeat this for each amount of ticks that we have. So this is the mesh line. So in this mesh line we will have this number of vertices, and the vertices will be starting at the start location, and they will have each segment of this mesh line will have the same length, which will be the position of the ticks that we will have. And on those points, on those vertices, we will add some instances, and each distance will be just a small cylinder, a curve line with curve to mesh and curve circle. I will not spend too much time here, just some cylinders that we created to place it on each of these points. So these are the ticks that we have. So now we have the color bar, we have the ticks, and we will now define the values. For the values, let's go here on values. For the values, we will create a repeat zone, and we will enter some value into the repeat zone, and we will convert it to us from string to curve, and then we will create the curve, and we will just join this geometry of each value. So how we do it? As an input, we have number of iterations, we have the range minimum and maximum, and we have the position that we will use to, as we showed before, to move all the geometry. From the number of ticks, we will enter this value as the iterations of the repeat zone. From it, and this will be also this ticks number, and which will be the maximum number of ticks we will have, range minimum and range maximum. The same computation we do ticks -1, and we will divide we will divide 1 over the number of ticks. Maybe I will have done on a different way with considering the 0.6, which is the size of the color bar, as we did before, but here I did just 1 over the number of ticks -1, and then we compute this value, which will be between 0 and 1. Yeah, so this is the number of ticks -1, and this is the number of ticks divided by number of ticks -1. So this will give us value between 0 and 1. So this will give us actually the current iteration, for example 1, 2, 3, divided by the maximum number of divisions that we will have. So if we map this value between 0 and 1 to the range minimum or maximum, this will give us these values. So this will give us 0.3. So that what we are doing is taking the range, the maximum and minimum range, and we will we are discretizing it in fixed number of values here. This is the value. This output from here, this result from here is the value that we have to convert to a string first with 2 decimal values. We can also add how many decimal values we want, and we will just convert this string to curves. This here we can choose with this node, we can choose the font, all the format of the text. And then what we will do is placing these values that we already compute from here on along this line here. So we will take the value that we have from here, that was from 0 to 1. So this was the position of the tick mark of each tick mark for each iteration, and we will multiply by the length of the color bar. We will choose the y coordinate, and we will not displace an x and y, and we will put it in the translation for each additional translation for each iteration. Then we add this node that is used for fill curve, which is this in order to not have only the border, but we need to fill the interior of the numbers. And here I'm adding some vector, and this vector will come from the position. So this is what allows me to vary the position of the whole geometry. Then every time I do a iteration, I will join the geometry, and this will be the output geometry of our values. That's all. This is what we have. We join the values on the ticks, and we set some material, which in this case is just a black material, and this is our output. Here we have the position. This is the input that I'm giving. If I change this here, just notice that I can actually change the position of all the color bar. As we define it like this. So we have almost everything from the project that we are doing now. We have built all the objects. We have creating the volume domain, the torus with the material that we see, and the color bar with the ticks. The last part we will do is creating empty axis, and we will add some custom properties to this empty. These custom properties will be some drivers that will control the parameters that we are giving to our visualization bundle. This will be very powerful because we will be able to control through these properties. We will be able to control the whole system. So how this is done? We have here the visualization driver, and we don't have any nodes here. The only thing we will have is here in the object properties. At the end we will have custom properties. Here we can add as much as we want, and we will define them, which is the name of the property, and which is the default value, and which is the range that we will have. This is very, very nice, very important for what we will be doing. So here in this gear icon, we see this is the type. It can be Boolean, it can be a string, it can be integer, whatever we want. And we have the minimum and maximum value, the step, precision, everything we can control from here. So we will create one for each property that we want to control through the on the visualization rig. Once we have done it, I have created one for an isotropy scale, one for range minimum and maximum, some ticks value, this threshold. I am not using it, but I created those an example. We go to the geometry nodes, and now we will see how we can link this to the visualization bundle. So here we can choose one of these groups. We need to do it for each time that we are calling this group node. We need to define the driver, unfortunately. But what we will do is just right click on the value, and we will choose here will be, for example, let's choose one that I'm not done before, add driver. So we will add the driver, and here we will choose which is the object that will have this driver. In this case, it will be visualization driver. Here we will use the single property, and here we will choose the property name. We will put it in squared brackets, and here we will put the name of the property. So I think it was thresh, and then like this. Just let me verify the name here in the visualization driver. Yeah, thresh. Then this will be already taking the values that I put on the threshold. So edit driver, again, this will be the way in which we enter the property name. Here we can do some math with some expression, some computation on the variable. So this var will be the one that we define here. As we wanted to pass it directly from the driver to the visualization bundle, we will just keep it as var. We can, for example, say var plus 5 or something that we want to control. This is very nice. And that's all. We will do it for each of the places in which, or the instances in which we are calling this VizBundle visualization bundle group node. So we call it here as an input for the Glyphs and so on. And we do it also for the volume domain. We see that here I'm also already all this magenta color means that we have already added the driver. And you see this is the variant or the variable that I'm placing here, and also here I can also add, for example, ticks. I didn't add here because I don't need to have control of the ticks, or I'm not using the ticks in the volume domain. But if we go to the legend and we see, for example, the ticks, and we see what we are receiving from the visualization bundle, I will just expand this. The ticks are marked as one of the drivers that we are getting. So I can do for all of them in all of those places, but I also can only define the drivers I will control at that specific instance in which I'm calling the visualization bundle. So here these are the three I need, so that these are the three I define as drivers. Let's test it. So this is everything from for the node creation. So this is everything that we need to do for this visualization rig that we created. Let's just test it. For that, I will go to the visualization driver. I can just right click here, area, duplicate area into a new window, so that I can just drag this here like this as I want, and I can change the values of what I have set on the driver. Isotropy scale, we say is this the size of the glyphs. We can put 10. I cannot put 10 here because if I see this is the maximum value. So if I put, for example, I want the maximum is 10. Now I can put 10 here, which is really big. I can put something more realistic, some more better to visualize tree, and I can change also the range of the mapping here. So 1, I changed this already. This automatically changed to 1. This will also reduce this area here. I have some small area here, but actually this is already extended to 1. Here 0, so we will see that it will start from 0, and we will adapt also the map range. We will adapt the ticks. We can change the ticks to be 10, and we will have all the 10 ticks here, or 4, and this will be automatically updated. 0.5. We'll have one region here without glyphs because there's no change, and 0.6. So we will have only, I don't know why I'm having these glyphs here. Maybe there is some overdetermination of the torus. Maybe we can try to fix that with the torus geometry. Let's see. Still there. Could be okay. Maybe this is because I have reached the limits of the volume domain. Yeah, that's the reason why. So I am changing here from something that is defined to something that is not defined. Let's just then move a bit the torus. This is the x, so we will put it 0 minus 0.18, and it's over. Yeah, we fixed it. And we can continue playing with our visualizer. This is very, very, very nice, very powerful. Okay, this is our result. We have built a visualizer, we have built a visualization rig completely on Blender 5. We have to go through different features that we can now use in Blender 5 that were not present in the previous versions, like the visualization, like the bundles. like the repeat zones and closures inside the shader or the shader editor. We have also used some drivers to control the parameters, and we have also used some of closures in some cases for the inside in the geometry nodes. We have used the volumetric grids, so the field on mesh, field on grid, sample grid, gradient. So we have made overview, first overview of which will be all the new features of the Blender 5. I hope you enjoyed this video as much as I did. I will leave the file in the description of this video. You can play with all parameters and make some different things. Let me know if you have some doubts. I will be happy to answer. Let me know in the comments what are you planning to apply, on which systems you want to apply this approach. And subscribe to the channel so you will not miss the follow-ups, the possible and future follow-ups of this series of videos with Blender 5.0. Thanks for watching until here, and see you next time.